Okay, here is, so we'll get into it. So we talked about pump curves, guys, and pump curves, if you remember, we had discharge on the x-axis, we had our head from the pump on the y-axis, or the system head, and the pump curve kind of looks something like this, just for a single pump. All right, and now we had our system curve as well. So the pump curve is something you get from the manufacturer, or you can test it. The way to test it is we have this lab, and I'll give you guys the data for it probably at the end of this week, where you have a pump, you measure the pressure and the discharge rate coming out of it. And then for different discharge rates, you measure the different, heads or pressure, and then you can create this pump curve. So then we have our system curve, and the system curve is some sort of, we'll call this the head of the system, and it's proportional to the square of the discharge due to the Darcy-Weisbach equation, or the Shazy equation. It's close to the square of discharge. So it's kind of like a parabola. It's a power law. And the way we make our system curve is, you have your pipes of a certain length and of a certain diameter and a friction factor, and maybe there's a delta Z involved. And you use the Darcy-Weisbach equation, or the energy equation, to create a relationship between the friction loss in the system, or the head that the pump has to overcome, and discharge. So for given discharge, you get this head loss, or the head that the system has to overcome. And so that's what this system curve looks like. And so where that system curve and pump curve meets, we get, what do we get? We get the match point, or the operating conditions. And so this is our Q, and we'll call it operating. And this is our head operating. And so for a given pump, right, and this is a pump, and maybe it's working at 1400 RPM, and it's got so many, horsepower or whatever, that pump is going to operate at a certain discharge rate for the system. So we put that same pump on a different system, that curve for that different system is going to look different. Maybe it's like this, and we're going to have a different match point. So same pump, different operating conditions, flow rate, and head. Okay, now what we're going to do is talk about our learning objectives. So we're going to say, given a pump characteristic curve, oh boy. For a single pump, we're going to calculate and draw the pump curve for two or more pumps in series and parallel. And so we're basically just going to be figuring out what it means when you put two pumps in series and two pumps in parallel or more, what that does to the pump curve. And so let's just define what series and parallel are real quick, and then we'll get into that. Let's see here. So pumps in series. So we have a pipe, we have a pump, And then we have another pump. So these are pumps in series. And then pumps in parallel, do in purple. So we have a pipe, it branches. So these pumps are operating in parallel. All right. Okay, go find Mama, okay? She needs to come down and help you. I'm teaching right now. Okay. All right. New schedule, handing kids off back and forth, and yeah, good times. All right. So let's look at just a system where the pump is working by itself. And we've got a reservoir. Actually, I'm going to erase this real quick. We'll start down here. So we got a reservoir, and it goes into a pump, and the reservoir goes up to another one. All right, and so our energy grade line, we'll do that in green. Goes to the pump, and it kind of comes down a little bit, right, in that pipe, and then it hits the pump, and then it goes back up, and then it comes down to hit the water level of the next reservoir. So this pump is pumping the water up. Hang on one sec, guys. Okay. Go upstairs, stop crying. All right, guys. Adventures. All right. We love our children. So here's our pump curve for this system. Here's our discharge, and here is our match point for the system curve. So the system with one pump is operating at these conditions. Okay. And then this would be our the head that this pump is adding to the system to provide the discharge rate that's coming out of here at that level. So now let's look at what happens when we do more than one pump. And we will start with pumps in series. So now we've got our little reservoir. We've got one pump, two pumps in series, and then they go pump up to the next reservoir. All right, so we start off with our energy grade line, and it starts to go down just a little bit. It hits that first pump, goes up, comes down a little bit, hits that next pump, goes up, and then comes down to the elevation of that next reservoir. Okay, so the way pumps, and this is pumps in series. So when we have pumps in series, when we have the discharge rate of two pumps is going to be equal to the discharge rate of one pump. Because they're in series, they're not increasing the discharge rate. But the head provided by two pumps is going to be greater than the head of one pump. But it's not quite going to be equal to the head of two pumps. And that's under operating conditions. So let's look at that on a pump curve. So here is our one pump curve. And then when we do our two pumps in series, what happens is we're simply moving that curve up. And the pump curve can actually double. So we're doubling the head for a given discharge rate. The head is 2 times for the actual pump curve and not for the operating conditions. So let's look at what happens with operating conditions. So here's our system curve. And if this was our Q under one pump, this is our Q under two pumps. Oh, wait. Two pumps. Okay. So I shouldn't say that discharge is going to be equal to. So the potential so the curve shifts up. Yeah. Let me just draw this a little bit differently. Sorry, guys. Okay, here's our one pump curve. Here's our two pump curve, like that. So you're just shifting it up, and I drew it a little bit offset, which is not correct. Let's do our system curve. So because anytime you move the pump curve, because you, in this case, increased the head for a given discharge rate, so if I were to just draw a line through here, the head is 2 times the head of one pump for that particular curve. So that curve, all we did is we took the pump curve, we multiplied all the y values by 2 to get that the shift up. But you see that the discharge rate doesn't actually change. So this is Q1 pump equals Q2 pumps for the pump curve, but not for the actual system. So we're kind of dealing with two different things here. So the pump curve shifts up vertically. And then now that because we have a new match point, with our new match point, this is our match point 1, this is our match point 2. So now we have obviously greater head and slightly greater we'll say the head is much greater and then the discharge is a little bit greater than Q. Or sorry, this would be 2. So that's pumps in series. We're doubling the head for a given discharge. And then let's look at pumps in parallel. So we'll draw our system here. Okay, so now we have our system, our energy grade line comes down, it hits those two pumps in parallel, it jumps up, comes down, And in this case, when we have two pumps in parallel, we're actually, instead of doubling the potential head for the system at a given discharge, we're doubling the discharge at a given head. So let's look at that, and I'll try to draw it better this time. Here's our one pump curve, and then now we're just doubling the discharge for a given head. So we're just kind of going out like that. So for a given head that this pump could provide, the potential discharge, again, not the actual discharge at the operating conditions, could be double. But now let's put our operating curve over that, our system curve. And in this case, our head increases a little bit, but our discharge decreases much more. Okay. So I will stop there. Do you guys have any questions about this setup? Sorry for the awkward note drawing. I'm going to be on paper hopefully by tomorrow or Wednesday. So I'll just to summarize that, for pumps, in series, this is where we have pump, and we double potential head at given discharge. And to create this curve, so you take one pump curve and double HP. So we just add or multiply the head of that pump for a given discharge. So if our pump curve looks like this, and then our head for a given pump is something like this. Then our head for, we keep the discharge the same, but for the pumps in series, we just double it. So we just do 1, 2, 3, 6. This would be our pump curve, same discharge. So same discharge, but now we double the head. So this is what our pump curve looks like for pumps in series. And then for our pumps in parallel, this is where we have, oops. We double the flow rate at given head. And so what this would look like is we have flow rate Q1, and I'll just do HP here. So if our head looks something like this, 0.51, 1.53, our discharge looks like this, 1, 2, 3, 4. Then under our two pumps in parallel, we get 2, 4, 6, 8. So we're just doubling the discharge. And that creates our pump curve. Okay, so we'll just do an example together, and then we can talk about other assignments and stuff like that. Okay, well, maybe I'll put the question to you guys. Why do we do this? Why do we care to, why don't we just get a bigger pump? Christian, I'll start with you. Why do we, would we do, for example, pumps in series?
Wouldn't it be more costly to fix a bigger pump than fix two small pumps? So that's why you would want to do it in
Yeah,
series.
that's could definitely be the case. And we'll look at pump costs for the projects. But yeah, maybe two smaller pumps are cheaper to operate and maintain or buy than one big pump. Val, what do you think?
In case one of them break, you have to have the other one working. Or if
So
you have one big pump, if it breaks, everything's shut down.
Yeah, exactly. So redundancy in the system, you have maybe one pump is just like not really running and the other one is, or maybe they're both running, and then if one breaks, you can still maintain some sort of flow rate and yeah, keep the system going. So there's a lot of reasons. Flexibility was another one, and I think you guys got at that in the quiz. The idea is we might have variable demands for discharge throughout the day. You could imagine in many scenarios where there's peak demand that we need to supply water to like pump a tank up really quickly during a certain part of the day, and then we can do it more slowly during another part of the day. So maybe we have different 3 pumps in parallel so that we can have them all running during the peak demand, and we can have one of them running during the low demand or something like that. Variable head situations could occur if you're pumping to a reservoir where the water levels are fluctuating a lot, then the head required to pump will change. So that happens in tanks and reservoirs, that sort of thing. So that's why we might have pumps in series to get that variable head demand. Okay, lost our iPad, hang on. Okay, so let's do an example. And this is example 5.4 in your book. So we're given a system, it's a reservoir shocker, and it goes, this is just our system, we'll just draw it without the pumps first. So we have a, oh gosh. So we have 10 meters, ooh, wow. 10 meters of elevation difference between those reservoirs. We have 300 meters of distance. We have some minor losses, a gate valve that's open. We have entrance and exit losses. And then we have a diameter of 0.4 meters, asphalt lined cast iron. I hope they don't use that anymore. That sounds terrible. And then our dynamic viscosity is given as kinematic 1.31 times 10 to the negative 6 meters squared per second. So we got to look up all these, like our E value based on that asphalt system. I don't have that in front of me, but we can look that up in our book. So first we need to do our system curve. What does this pump have to overcome? And so our system curve is, we just go to the energy equation. And we'll write out our energy equation as, so the pump obviously will go somewhere in here. So because we're going to evaluate between the free water surface, we're only interested, we have to overcome the delta Z, and then we have to overcome the friction in the pipe, right, and the minor losses. So on, we'll say Z1 plus HP, so the pump goes on the right side, is equal to Z2 plus our friction losses, which will be major and minor. And so to write the system curve, we just have to put it in terms of HP. So this is HP system. The pressure that the pump has to overcome is going to be equal to delta Z plus HF. So this is typically what your pump curve equation will look like, or sorry, your system curve equation will look like. Okay, so let's write that out a little bit better. Our Darcy-Weisbach equation plus sum of our minor loss constants, V squared over 2G. It's just one pipe. It didn't get bigger or smaller, so we're not dealing with different velocities. So we'll just put our numbers in here. So 750 is going to be our length of our diameter. And then we'll do we add up our sum of Ks is going to be equal to 1.65. Sorry. Okay. And now this is actually fairly easy. We can use, let's see here, Swami chain velocity. Okay, great. So we don't actually need to do like Moody diagram or anything like that. We can use our Swami chain equation. I need to get a smaller pen size here. So we could do this in Excel. That's probably the easiest to do. So Q, and then we calculate our velocity because we know the diameter. Then we can calculate our Reynolds number because we know velocity and the diameter and the kinematic viscosity. We can do F using Swami chain, and then we can calculate our HP in meters from this equation that we wrote out up here. All right. So all you do then is, we don't need to figure out what the discharge rate is. We just need to give it a discharge rate. So we'll start with 0, and then we can just do some increment. And you don't want to get too coarse because you want to be able to find that intersection, which we're just kind of mostly going to be doing by eye because this is be hard to, not impossible to solve, but harder to solve on paper to solve these as a simultaneous equation. So I'm just going ahead and solving this. We, Q is equal to VA, right? V is equal to Q over A. So Reynolds numbers, I'm not going to put those in there. This is from the Swami chain equation. We can throw in our Reynolds number and calculate pretty accurately the F value for a given Reynolds number. And then we get our HP. And so HP, again, we just solve this equation with all these values. So F and V. And we end up with 10.0, 10.5, 14.0, 20.7, and then 31.0. So you can see this as you increase the discharge, we're kind of a quadratic equation. So we're starting to increase non-linearly in terms of the head that the pump has to overcome. Okay, so now the next step is we're given a pump curve. So we're saying, okay, we're going to use this pump. So let's figure out what the match point will be for pumps in series and pumps in parallel. So here's our one pump curve. And then we'll do our system curve. So it starts at 10. So 10 meters is basically when nothing's running, we have that head difference of 10 meters. So when there's zero discharge, we have that 10 meter, the pump would, for no discharge, the pump would have to overcome 10 meters. So that's 10, and then the system curve would look something like this. We'll just draw it generically, but you can plot this in Excel. So do meters, and then okay. So now we'll do let's do series. So two pumps in series, and we're just going to add or we'll multiply the y values of that pump curve by 2 to look something like that. Maybe we'll just make it go down just for illustration's sake. Okay. And then we'll do our parallel, so two pumps in parallel. And that's going to just extend this out. We do the x values by 2. So we multiply the x values by 2. So here's our pump curve for 2 in series, and our pump curve for 2 in parallel. And then we have our different match points. So here's our match point for one pump. This would be our match point for 2 pumps in series. And then this would be our match point for 2 pumps in parallel. So then we have 3 sets of operating conditions depending on how we design this system. So for this particular problem, I'll just give the what we end up with. So if we have Q of one pump is going to be equal to 420 liters per second. So we're working in liters per second now. The head of one pump is equal to 18 meters. So this is the operating conditions. And then our efficiency, and we'll look at efficiency curves for the project. Our efficiency would be 40%. So for every pump curve, there's also an efficiency curve. And I'll do that in orange. And so that usually looks something like this. And so there's some maximum efficiency that's usually somewhere in the middle of that pump curve. So depending on where you are in that pump curve, you'd have a different efficiency value. So if we look at our operating conditions under series, so 2 under series, then we would have slightly bigger, so 470 liters per second. Our head ends up being 20 meters, and then our efficiency is equal to 15%. And then 2 in parallel. We get 590 liters per second. Our head is 26, and then our efficiency is 62%. So obviously a greater efficiency, but because we're using 2 pumps, we're probably using more energy. But that's just another factor to take into account when we're trying to design a system. So for this particular pump, in the system curve that we have, you end up with bigger discharge and head provided. So complex relationships, you're not going to get double the head given your system for pumps in series or double the discharge for the system given 2 pumps in parallel. The relationships are going to vary depending on what the shape of the pump curve is and the system curve. So that's all I've got. I'll take any questions that you guys have. Okay. We will have you guys give you pump curves